Hi, these are edited versions of the lectures that I taught synchronously over Zoom. I hope you find them useful. All right, so today we're going to have our lecture number 15. It's going to be on HAC Covariance estimation, where HAC here stands for heteroscedasticity, autocorrelation, consistent estimator of the variance. So, and that's going to be it. So, last class, if you remember, we talked about heteroscedasticity consistent standard errors, or we call them also robust standard errors, or white standard errors, or Eker, Hoover, and White standard errors. All those names meant the same thing. And we show that the main result that we derive is that the standard errors were consistent under the same conditions that you have for deriving asymptotic normality. And after that, we discuss some popular finite sample adjustments. These are, as we said, adjustments that try to bump the standard errors up, the residuals up, because these are known to be too small in finite samples. And then we discuss where that intuition is coming from. And in order to do so, we talk about the variance-Fisher problem, which is an agent problem about testing the mean of two normals, where all these heteroscedasticity consistent and finite sample adjustments make a lot of sense. Today, we're going to talk about stationarity, and we're going to talk about essentially, it's going to be the only class that I'm going to deal with time series. And so we're going to have to get some basics about time series, which is going to be parts of today's class. So we're going to have to talk about stationarity, and that's going to be important to be sure that we are estimating something, an object that is well defined. And then we're going to talk about summability and mixing, which are going to be the conditions that are going to give us a law of large numbers and central limit theorems. And then we're going to be ready to discuss estimation of the variance when there's autocorrelation. And we're going to discuss some naive approaches, and we're going to see how or why. We're going to quickly try to think about weighting and truncation. And we're going to prove at least a sketch of a proof. It's going to be heuristic, but at least hopefully we'll give you the main elements of the arguments behind an actual proof that the HAC covariance estimators are consistent. Okay, so that's the plan for today. The setup is going to be the same as we've been dealing so far. So the first, 3 bullet points are the same. We're going to have x, y, u. We're going to have beta as before. We're going to assume expected value of xu is different than equal to 0. No perfect collinearity, and so on. So up to here is where we have done so far. By now, you should know this by heart, I guess. And today, we're going to deviate from when it comes to the sample that we obtain. We're going to assume that we have observations that are not necessarily IID. Okay. So in particular, we want to have dependence across observations. And today and Thursday, we're going to cover this case. But Thursday is going to be different in 2 dimensions that I'm going to explain on Thursday. Today, we want to think in particular about the case of autocorrelation, which is the case where xi and xi prime may not be independent. Okay, so as you see, the usual notation when it comes to time series is always to index things by t, right? Time. I'm not going to do that because I'm not going to deviate from what I've been doing. So I'm going to be indexing observations by I. We're going to assume that the observations are naturally ordered, okay, as I said, it's in time series. So you have an observation xi plus 1 comes right after xi, okay? If this were like individuals, of course, the order is arbitrary, but here we're going to have, again, think about time series. And what we want to do is to think about 3 things, or 2 things I wrote here. Let's just respect what I wrote. I said, A, we need appropriate law of large numbers and central limit theorems. We're going to have averages. We want those to converge where we want, and so on. But now we need new versions because we have things that are dependent. But also importantly, we want a description of the object that we want to estimate. Okay. The minute that the data is not IID, the independence is fine, but sometimes you could have no identically distributed random variables, And so, it's not so obvious what you may mean by mean, because, they may have different means. And so if we want to estimate the variance, what is that variance? So we need to sort of like be clear about what we are estimating. So we're going to do these two things simultaneously. So let's think about it. Okay, we're going to think about law of large numbers first. So when the data is IID, okay, think about here. So let's x, for now, as I said, I want to focus on a scalar x because this is makes things easier. So x is scalar. Forget about the regression part. Let's just look at a random variable. And then when x is IID and it has mean mu and variance sigma square, you have that the variance of the sample average, okay, which is 1 over n sum of xi, is as 1 over n squared sum of the variance of x. And so this is sigma squared. You have n terms, and you end up that the variance is sigma squared divided by n. And this goes to 0 because it's divided by n. And so when you try to show that the sample average is consistent for the mean, you want to check that the probability of x bar n is greater than epsilon. Okay, and this is less than or equal by Chebyshev inequality to the variance of x bar n divided by epsilon square. And this is just sigma square n divided by n epsilon square. Done. You have consistency. As I said then, the law of large numbers in the ID case follows by an application of Chebyshev inequality. And why is that? Because the variance of the sample average goes to 0. Okay, and that's what's going on. The problem is that without the independence, okay, we will need additional assumptions to control the variance of the average, this variance over here. And so we're going to start with two assumptions that, as I said, are going to be part of making sure that the objects that we want to estimate are well defined. The first one is the concept of strict stationarity. It says a process, okay, now we're thinking about time series case, xi from 1 to n, is strictly stationary if for each j, the distribution of xi through xi plus j is the same for every I. So the way to think about that is, take j equal to 0. You're saying the marginal distribution of each observation is the same. Then take j equal to 1. Then you have two pairs of observations that are consecutive. The joint distribution of x1, x2 is the same as x2, x3, as x3 and x4, and x4 and x5, and so on. You grab two consecutive observations. It doesn't matter where you place those two in the sequence. The distribution is independent on where you place them. And then if you grab three consecutive observations, the same. Is that the location of where you grab these three observations doesn't affect the distribution of the three observations. And that is the concept of strict stationarity. And then we say a process is weakly stationary if the mean, the variance, and the covariances between observations do not depend on I. Okay? So here you're saying all the variables have the same mean, the same variance, and the covariance only depends on how far the observations are apart. So xi and xi plus j. So the covariance actually depends on j, of course. So if you grab two consecutive observations, it could be some covariance that is going to be gamma 1. But if you take x1 and x4, for example, that's going to be gamma 3 because there are three observations apart. And then, this object over here, the mean, is mu. So it's just saying, for example, that if we are interested in estimating the mean is well defined because all these observations have the same mean. Okay, so stationarity means that the unique mean is well defined. We're thinking about estimating the mean here again. So what's the variance of the sample average? Well, look at this. The variance of the sample average now is, you pass the variance. You have 1 over n squared, the sum over I, the sum over k, and the covariance of xi, xk. Both of the sum go from 1 to n. And so what are these covariances? Well, when k is equal to I, you have this gamma 0, which is the variance. So remember, in our notation, gamma 0 is the covariance between xi and xi, which is no other than the variance of xi. And so we have n of those terms. And then when k is equal to I plus 1, okay, you have gamma 1. And how many terms do you have? Well, you have n minus 1 of those. And then, when k is I plus 2, you have gamma 2. How many terms do you have? Well, 2 times n plus n minus 2, and so on. And then you keep going. And then you write this expression, and it's equal to 1 over n. You're going to take one of these n squares and put it inside. So you have 1 over n. Now you have gamma naught here, which is the variance of the observations, plus twice the sum from 1 to n of the gamma j's, okay, times 1 minus j over n. So here we're using this notation for the gamma j's, which are the so-called autocovariances. And remember that gamma 0 is just the variance of x, okay? So if we want to use an argument like Chebyshev's inequality, like we did before, we need the variance to vanish, okay, go to 0 as n goes to infinity. And in order for this to happen, you need that the last summation that we have over here does not explode. And that's what is called absolute summability. This condition over here that says that if you sum the absolute value of these covariances from negative infinity to infinity, that is finite. What does this mean? It means that you can allow observations to be correlated to each other as long as they are not too far from each other. But the minute that the observations are really far from each other, okay, or this gamma j for some large j, then that is essentially really small. Let's say 0, okay? And so when you sum all these covariances, these are finite. And then you can see here that if this is finite, this sum over here is finite. And then, this is finite by assumption because we're assuming that we have finite second moments. Then you're dividing by 1 over n. 1 over n times something that is finite will go to 0. And so, as I wrote here, a law of large numbers now follows from an application of Chebyshev's inequality, like before. Okay, so lemma. If xi is a process that is weakly stationary time series, okay, with mean mu, and is absolutely summable, has absolutely summable autocovariances in the sense that I described before, then a law of large numbers holds in probability and in L2, essentially by the proof that we did before using Chebyshev's inequality. Know that just assuming stationarity is not enough because stationarity doesn't guarantee that the sum that we had before will be finite, okay? And an easy, silly example would be that, here you have a random variable psi that is just standard normal, and then imagine your observations are all equal to psi for all I, the same random variable. Okay, then of course they are stationary because the distribution is the same for any pair, any triple, or whatever. But the covariance between any two observations is just going to be 1 because they're exactly the same observation. Okay, and this will not be summable because you're just going to be summing an infinite number of ones, and that's going to be infinity. Okay, so this is then the law of large numbers, and I want you to keep in mind that we need stationarity, some form of stationarity. Weak stationarity is enough, and then we need summability. So one question you can ask is what gives summability? Summability looks like an sort of, in a way, abstract condition that is saying that certain things don't explode. And as I said, intuitively, it may mean that, or it means that you don't have enough dependence, or you have enough independence, if you want. So what would be a condition that will give you something like this? Well, there are a lot of different conditions, and I don't intend in this course to cover any of this. Plus, I don't, I don't even view myself as somebody who knows a lot about this. Okay, but the popular conditions that give you this are called mixing conditions. Okay, here I'm going to present one. There are many others. There are beta mixing and have different names, but the simplest one probably is this one called alpha mixing. So let's see what it says. We say that absolute summability from mixing assumptions. Okay, and so alpha mixing means the following. Assume that the sequence xi, okay, is alpha mixing. We say that let alpha n be a number such that the probability of the intersection of the events A and B minus the probability of A times the probability of B is less than or equal than alpha n for any event A that belongs to the sigma algebra generated by x1 to xj, and B belongs to whatever is generated by xj plus n, xj plus n plus 1, and so on. Okay. If alpha n goes to 0, okay, as n goes to infinity, the sequence is said to be alpha mixing. So this may look obscure at the beginning, but let me remind you of two things. First, if A and B are two events that are independent, okay, the probability of the intersection is the probability of A times the probability of B, right? That is basic material. That's sort of like a definition that you know when you took your first probability class. And what is this saying? This is saying that this difference, right, which is the difference between, say, being independent or not, cannot be too big. It's bounded by alpha, and alpha is going to 0. And what are these events? These events are things that depend of x up to xj, A, whereas B starts from j plus n. So these are separated by jump of size n. The last one you have in A is xj. Suppose j is 10. Okay, suppose that n is 5. The first one that starts in B is x15. So they're like n apart. And so you're saying any event that depends on these j observations, and any event that depends on observations that are n apart from these observations are, you're saying, close to being independent, at least as n grows, okay? And then you're pushing these things apart, farther apart. And so eventually, imagine if alpha is literally 0, then you're saying that these two things are independent. So this definition of alpha mixing captures this intuition that we said before, that the farther apart the observations are, the more independent the observations are. And we're going to be assuming mixing today. Again, why? Because mixing is going to give us some ability. So now we're going to go back to say, well, we want to estimate the variance, okay, in the case where we have time series, okay. And so, but the question is, what is the variance? What does it look like now? And I'm going to say, remember that we typically normalize the sum, okay, in such a way that the variance is 1. So we just do square root n, 1 over the square root n, the sum, okay. And so if later on we use things like t statistics, where we're going to standardize, we're going to get something that is going to have asymptotic variance equal to 1. But in order to do that, we need to divide by the right square root. And so notice then the variance of 1 over square root n, the sum, which is the object that will appear in a center limit theorem statement, is, according to the derivation that we did in the previous slide, is gamma naught plus twice the sum of gamma j, 1 minus gamma j, divided by n. And if you just take this to infinity, what you obtain is this expression over here. And I'm going to call this limiting object omega. And omega is now the limiting variance of a scale sample average when the observations are dependent. Okay? And this is going to be finite as long as we assume that this sequence is summable, or alpha mixing conditions. Okay? And this is called the long run variance. So there are many center limit theorems for serially correlated observations. Below, I'm going to show you a version that is coming from this book by Billingsley. By the way, today's lecture, since this is not a topic that you're going to find in a lot of the references that I gave for this class, follow this book, the lecture notes by Hansen, and some lecture notes by actually Anna Mikusheva at MIT, who she wrote really clear notes on this. So I'm basing all today's lecture on these sources. Anyway, theorem says, suppose that x is 1, strictly stationary, 2, alpha mixin. 3 has 2 plus delta moments, finite. And fourth, you have that the alpha in the alpha mixin goes to 0, but actually goes to 0 at a certain rate. That gives you this sum over here. I'm not going to explain. This is just a condition that appears in the proof of the CLT that I'm not going to derive today. But if you have these 4 conditions, then you have a central limit theorem for dependent observations. Okay, that says that 1 over square root n xi converges to a normal with mean 0 and variance equals to omega, where omega is the long run variance in the previous slide. So now we have CLT and we have a law of large numbers. And with these 2 tools, we can go back to the regression framework and think about how we do inference in a regression where we have dependent observations. Do you have any questions about this? All right, let's keep going. Now we're gonna try to talk about what the topic is for today, which is estimating these long run variances. We're gonna go back to the linear model. And when we have time series, and we had some discussion of this already when we talk about panel data, saying that the expected value of UI, say conditional on xi, if we have 0 mean independence type of assumption, is 0 is not enough. Okay, I wrote here when the data is potentially dependent, say time series, panel data, cluster data, we have to describe the conditional mean relative to all variables that may be important. Okay, and in particular, you say that x is weakly exogenous if the expected value of UI, condition on xi, and all the history of the x's, xi minus 1, and so forth, is equal to 0. Okay. And again, here I repeat, because it has to be clear that we're assuming that we have a natural ordering. Okay. I repeat this today because on Thursday we're going to have a case in which there's not going to be such natural ordering. So the least squares estimator of beta is the object over here. Nothing changes. It's the same thing that we always have. Square root n beta hat minus beta. It's just the usual x prime x inverse. And then we have 1 over square root n x u. And so now we want to derive the limiting distribution of the least squares estimator when we have time series data. So when you look at this expression, there are actually 2 random variables here. One is, so the x's over here, and the other one is the x times u, which I'm going to call here eta, okay, for simplicity. It's going to simplify a lot of the arguments. And we're going to realize then that what we need are stationarity and summability or mixing conditions for x and eta. In particular, we need a law of large numbers for the x's, okay, or the x's square, and to obtain this result. And we need, to apply the central limit theorem that I showed before to eta to obtain this result. And we know what the limiting variance is going to be. It's just going to be omega as described in the previous slide. So today I'm going to do a couple of simplifications, just because, again, it's going to be heuristic, but I want to just give you the main intuition behind these arguments. The first one is I'm going to assume that this eta over here is scalar. Okay, so it's x is scalar. Of course, everything will go through for vectors, but then I need to, the notation is just more annoying. I don't want to get into that. And the second one is that when we talk about an estimator of the variance, I'm not going to deal with the residuals. So, okay, I'm not going to deal with u hats. I'm going to assume that we observe this eta, okay, which is as the real use. And you know from proofs that we did before that replacing the use with the u hats is going to entail doing arguments like we did last class, which, again, I'm not going to focus on those today. They are not the same. They're more involved because we don't have IID data, but it's just going to require the same things that we did last time, which is you have u hats, you add and subtract the use, and then you just claim using some tools that the difference between the true use and the u hats is 0. But for now, let's think about this. So what is the limiting distribution of least squares? Then it's just it's normal with mean 0 and variance sigma x inverse omega sigma x inverse. As always, by now we should be used to this. It has a sandwich form. And the sandwich has the bread, which, as I said, is always easy. And actually, it's the same object that we had before, so nothing changed. And we have the meat. And the meat is actually quite different than what we had before, okay? Because in this case, you can write the meat like this, okay? Multiple ways of writing it. I wrote it in a slightly different way before, but it's just an infinite sum of autocovariances. And I wrote this long-run variance is significantly harder to estimate than the usual variance-covariance matrices that arise under IID assumptions. And today we're going to try to figure out how to estimate omega. And this is so-called heteroscedasticity autocorrelation consistent approach, okay? Because what we're going to do is trying to capture both, okay? And as I said, the simplification that I'm going to make is I'm going to ignore the fact that in practice U will be replaced by a regression residual U had. And also I'm going to assume that eta here is a scalar. I should write that so that you have it recorded. Eta I scalar. This is another simplification. All right, so we're going to start with what I call a naive approach. Okay, the naive approach is just saying the following. Omega is the sum of all autocovariances, an infinite number of them, okay? However, for a given sample, we can only estimate n-1 autocovariances, okay? And so the idea one, or the naive approach, is what if we just use the ones we can estimate, okay? And those are just gonna be gonna lead to this estimator. Omega tilde is just the sum from j equals to negative n minus 1 to n minus 1, and then omega hat j, and omega hat j is just gonna be 1 over n, sum from y to n minus j. Okay, so you're saying I need an infinite number of autocovariances. Of course, I cannot estimate an infinite number of autocovariances, and then I'm going to just estimate as many as I can, which are n minus 1. So let's see what's the behavior of this estimator that estimates as many covariances as you can, which I'm calling here the naive approach. So presumably it's not going to work really well. But what we would like is for this guy to be consistent for omega. Okay, so let's see. Omega tilde here is the sum from j equals negative n minus 1 to n minus 1 of gamma hat j. And I'm going to replace gamma hat j by what it is. Oops. Sorry. And so this here, you can write as 1 over square root n, sum from 1 to n of eta I, or n minus 1. And this conversion distribution to a normal, which means 0, and variance omega. And so this naive estimator, which we hope that could be consistent for omega, actually doesn't converge in probability to omega. It converges in distribution to a normal that is centered at, sorry, this should be square, and this should be square. Okay. There we go. It converges to the square of a normal random variable. Okay. And so the estimator is inconsistent. And the problem is that this estimator estimates too many autocovariances that are really poorly estimated. Because I said you can estimate n-1 autocovariances, but think about gamma hat n-1. How many observations are you using to estimate gamma hat n-1? Well, if you just look at gamma hat n-1, it's just going to have eta 1, eta n. That's it. It's one observation. Okay, and so you're estimating a lot of covariances that are really poorly estimated because you have very few observations. And as a result, the estimator is so noisy, okay, that instead of being consistent for omega, which is the object that we want, it just converges in distribution to a random variable that, you know, is going to be something like a chi-square thing. But it's just the square of a normal. So this approach doesn't work. Okay, so one way to deal with that idea or with that problem would be to say, let's use truncation. Okay, so we cannot estimate that many covariances. So why don't we just truncate and we estimate just covariances that we think that we can estimate sufficiently well? That would give us this estimator that is called omega bar, which is now, instead of summing from n-1 to n-1, it just chooses some threshold that we're going to call mn today, and it just sums from negative mn to nmn. Okay, so mn is going to be a tuning parameter later on, but let's say it says 5. So you estimate 5 covariances, and as I said, and I said this multiple times, we can rewrite this as gamma 0 plus twice, just considering the positive gamma j's. Okay, and we're going to be using this representation later as well. So mn here has to be something smaller than n. And then we're going to do asymptotics where we allow to consider more terms as the sample size increase. But we really want this truncation to be small. And that means that m divided by n goes to 0 as n goes to infinity. So this idea, okay, has 2 properties. One is that you can show, as I wrote here, that it's going to introduce a finite sample bias. Okay, why? Because you're going to be not estimating all the covariances that you need. You're just going to be estimating some of them, and that's going to give you a bias. And so as m increases, okay, the bias is just going to be smaller and smaller. So if you just care about the bias, you want to let m be big, but you don't want m to be too big because of the problems that we just described in the previous slide, which is then you're estimating too many things with noise. And so that is a problem, and we don't want to sum up too many noises. So at the end of the day, you want some m that is not too big so that you can get consistency, but big enough so that you don't have a lot of bias. Okay. And then the other problem that we have here, that this estimator could be negative, okay, which is an estimator of the variance is kind of unpleasant, right? That you have an estimator of the variance that you obtain a negative number. And you say like, well, how could it be that this is negative? Well, suppose that you take m equal to 1, okay? And so the estimator here at the top is just going to be gamma hat 0 plus 2 gamma hat 1. Well, if you have that this autocovariance is sufficiently negative, in particular smaller than 1/2 gamma hat 0, then this estimator will be negative, okay? Of course, the true sigma is not negative because the true sigma is adding other gammas, gamma 2 and gamma 3 and so on, and those, you know, may be positive and bringing the omega back to being positive, but the estimator here could be negative, Okay, and when you think about matrices later on, this is not necessarily positive definite. So this is a problem because it's kind of unpleasant that you just compute an estimator of the variance and you obtain a negative number. Okay, so truncation sort of like has some hopes to work in the sense that we can have something that is consistent, but it has these issues that introduces a bias in finite sample and that it gives us a negative estimator, okay, or potentially negative estimator, I should say, not necessarily negative. So the proposal then in the literature was to add something else on top of truncation, and it was to add weighting and truncation. And if you add weighting and truncation, you get the so-called HAC Covariance estimator, which was proposed by New and West. And so the idea is to create a weighted sum of sample autocovariances with weights guaranteeing that the object that you obtain is positive definite. And this estimator that now I'm going to call omega hat n is just positive by construction. And it has goes back to, in a way, summing all the autocovariances, although in a minute we're going to see that that's not necessarily true, but just for this expression, look at it like that. And then it has the kernel here, right? This K here is the kernel in the same way we use the kernel in non-parametric regression, okay? And this is weighting, okay, all the autocovariances. And the idea is that you're going to put more weights to gamma hats that have a small value of J because you think that you can estimate those well. And you're going to put low to zero weight to gamma hats that are associated with a large value of J, okay? What we're going to need are conditions on M, which is now still called a truncation lag, but it's also, as you can see, the bandwidth of the kernel. And on the kernel, so that we obtain consistency and positive definiteness. First, we're going to need M to go to infinity, but not too fast. This is something we saw before. And today, I'm going to require this condition. M cubed divided by n goes to 0. Okay. Why? Because this is going to be simplify the proof that we're going to do. If you just go to the original papers and then you go to more formal arguments, you can show the results only requiring m squared divided by n going to 0. But we're not going to get into that. Second, we're going to need that the kernel K guarantees that you have something that is positive definite. Okay. And that will mean that it requires that these things are weighting high lags, small weights on high lags, and also that when you as n goes to infinity or mn goes to infinity, that for a given fixed J, say the first autocovariances, eventually you give it full weight. Okay, so that's sort of like the conditions that we're going to list. And as I wrote here, as with now non-parametric density estimation, there is a variety of kernels that satisfy all the properties that we're going to need later on. Okay, but as it is typically the case, the kernel ends up mattering less than the choice of this truncation lag, mn, or bandwidth. Now, in terms of what are perhaps the popular kernels, here I'm giving you 3. The first one is called the varlet kernel or the triangular kernel. That was the one proposed or used by New West in the original paper. It's just very simple. Is 1 minus the absolute value of x. And here in this picture is this red line that you see is a triangle because this is only one side of the kernel. The other side is symmetric, right? So it looks like a triangle. Truncation, which is the idea that we discussed early on, is something that gives weight equal to 1 and at some point just gives weight equal to 0, which is over here. There's also something called the Parsons kernel, which is this one over here. Looks like it's the green one here, but it looks like a normal type of weight, but at some point it's 0. Okay, so it looks like this, but then it's 0. And then there's one called the quadratic spectral kernel, which takes this like funny form. And then is the one here sort of like darker, which looks like a normal, but it becomes negative at some point, and it has sort of like a sine wave, or I wrote here a damp sine wave. Why do I show a kernel like this? Because this was shown by Andrews in a later paper in 91 that it had some optimality properties. Okay. In practice, if you just look at again what the default is in a lot of packages that you can use to compute HAC standard errors, you're going to see that this is still today a default. And as I said, I'm not going to comment much on the choice of the kernel, but I just want you to have a sense of what they look like. Okay, they're all symmetric about 0, and this is a condition that we're going to need. The first two have support on 0, 1. Okay, you not in this picture is 1.5, but it doesn't matter. But it's negative 1, 1, and the quadratic spectral kernel is has this sine wave. So when we do the proof in a minute, we're going to just focus on kernels that look like this, that just have some weight and then 0, because that's going to also simplify the proof. The first two, the weights assigned to gamma hats decrease with the absolute value of j, and at some point they become 0. Okay, again, look at the triangular one. It just has a decreasing weight, and at some point it's just 0. Okay, so in those two kernels, m is actually the so-called truncation lag, whereas the quadratic spectral, it has positive weights or even negative weights after the truncation lag. So certainly this kernel over here is slightly more difficult to interpret and also to analyze. Not significantly, but we're gonna ignore it for now. So these are the weights that we can use. And so, as I said, we're gonna focus on the first two kernels. And for the first two kernels, we can just truncate, okay? We can write them like this. And this is the estimator that I'm gonna focus on today. This is the estimator that we wanna show that it is consistent for omega. And notice that it doesn't sum all the covariances, it just sum m of the autocovariances, and it doesn't just give weight equal to 1 to all of them. It uses these weights given by the kernel here. So it looks like the truncation idea, but it's adding weight to that. And the theorem says the following, and this is what we're going to do for the rest of the class. Is going to prove this theorem, and then we're going to discuss it and go home. Assume that eta I is a weakly stationary sequence with mean 0 and autocovariances given by gamma j, which is the covariance of eta I and eta I plus j that satisfy absolute summability. Okay. Assume that mn goes to infinity as n goes to infinity, and as I said, m cubed divided by n goes to 0. When assume that the kernel maps negative 1 to 1, is 1 at 0, is continuous at 0, and is symmetric. Okay. And then for all j, the sequence, this zeta ij, which is going to be eta I plus j minus gamma j, is stationary and satisfy this uniform summability property. This object is weird. It limits the dependence of these random variables that are the product of the etas, and we're going to use this at some point in the proof. But if you have 1, 2, and 3 plus the summability condition stationarity, you have that the HAC covariance estimator is consistent. And whereas last class I emphasized how we were able to prove the consistency of the robust standard errors under the weakest possible assumptions, today that's not the case. Okay, we are adding some conditions like this one that are making the proof simpler. But we're at the same time dealing with something that I don't emphasize in this class, which is dealing with time series. So that's why I'm giving priority to the simplification in the argument and to the generality of the result. But you can see also that how you need a lot more requirements, okay, to get consistency of this type of standard errors relative to the ones that we covered last class. So let's work on this proof. We're going to prove again that this guy over here converges in probability to omega, which is the sum of the infinite autocovariances. All right. Any question before we start working on that proof? All right. So let's now work on the proof. The proof is going to be somewhat heuristic, and it's going to be centered around this case where 8 is scalar and so on, but it's going to have the main components. It's going to take us like 5 steps perhaps to do it, okay? But hopefully each step is going to be clear and it's going to build up to the result. So we're going to start with this. We want to show that this estimator over here converges to this one. So I'm going to start by working out this expression and rewriting this difference in a way that is easy to work with, okay? So I'm going to write the following. Omega hat n minus omega is, let me replace sum j negative mn, the kernel, j divided by mn, and gamma hat j. And then we're subtracting omega, which is an infinite sum. And what I'm going to do is I'm going to add and subtract an object that, is going to help me with the analysis, which is going to be the same type of estimator, but that instead of using gamma hats, just uses the true gammas. So I'm adding and subtracting that. And now I'm going to group the terms. And the first thing is just going to be the sum of all the, say, absolute values of j greater than mn, gamma j, plus the sum of j negative mn, mn k minus 1 gamma j plus the sum j negative mn, the kernel, and now we'll have the difference between gamma hat j and these gamma j's that I added. And I'm going to say this is what I'm going to call term 1. This is term 2. And this is term 3. And then note, I'm going to write here. Term 1 goes to 0, as then goes to infinity by summability. So the first term is just really easy because we're assuming that the gammas are summable. So it just goes to 0. And term 1 is, I'm going to say, if you just want to give interpretation, term 1 is the error due to truncation. We're truncating. And so what is term 1? It's telling you where you're missing some elements. You're missing all the gamma j's that come after mn. Okay, those are there. That's an error due to truncation. What is term 2? Is an error due to weighting. Right? Because if you look at this expression, it's the difference between the kernel and 1, which is what you would do if you were not weighting. So it's an error due to weighting. Okay. And then what is the error? Term 3 is, in a way, the error due to estimation. of gamma. But another thing to note, which is the term that we're going to analyze next, is that term 2 is not stochastic. Or non-stochastic, let's say. Non-stochastic, as term 1 was. So one easy thing about this decomposition is that term 1 and term 2 are non-stochastic. They're not random. It's just, deterministic sums. And so, then you can say that something converges to 0 like this. We're not saying converges in probability or anything because it's a non-random object. Okay, so it just goes to 0 as n goes to infinity, because mn goes to infinity as n goes to infinity. Okay, so I didn't write it down, but this follows from mn going to infinity, right? We need that. We need that and some ability. So the proof is just let's analyze term 1, term 2, and term 3. Term 1 is done. So let's take a look at term 2. Okay, the error due to weighting. Well, here's the decomposition we just did, and this is what we just call term 2. And now let me define two objects here. The first one is this function fmj, which is the absolute value of the kernel minus 1 times the absolute value of gamma j. And notice that this function fn is less than or equal than a function that I'm calling g, which is just twice the absolute value of gamma j. Why is that? Because the kernel is bounded, I'm going to say here, because the kernel is bounded by 1. This sucks. Let's write it better. Also,
one question.
Yeah.
You said term 1 is stochastic, but term 2 is not?
No, I said term 1 and term 2 are non-stochastic. Term 2 is non-stochastic as term 1 was. Or let's write same as term 1. So here also note that this function g is summable. Because gamma j is summable. Okay, so I want to show that the second term goes to 0. Okay, and then in order to do so, I'm going to use this notation that I introduced. The fn function, the g function. And so I'm going to go as follows. I'm going to say the absolute value of the sum of j negative mn k j divided by mn minus 1 gamma j. This is less than or equal than the sum from negative mn absolute value of k j m minus 1 times the absolute value of gamma j. And this is the object that I just called fn of j. So we're right here is the sum mn to mn of fn of j. I'm going to say here, note that fn of j converges to f of j, which is equal to 0 for all j, as n goes to infinity. So point-wise, fn of j converges to fj of 0 because the kernel at 0 is 1. This is what we discussed before. the kernel at 0 is 1. And then for any given j, if you have j divided by mn and mn is going to infinity, the kernel is conversion to k0, and k0 is 1. So you have 1 minus 1, and that's 0. So then this converges to the sum from negative infinity to infinity of fj, which is 0, by the dominated convergence theorem. Remember, dominated convergence theorem tells us the sum of a function converges to the sum of the pointwise limit of the function, which is this f, if the function that we're dealing with is dominated by some other function that is summable, which in this case happens because fn is less than or equal than gj for all j, and we said this function is summable. So the function fm is dominated. It converges pointwise to 0. So the sum of this converges to the sum of 0, which is 0. And so the result follows, and the second term goes to 0. And here we use that, the kernel was bounded by 1, that gamma was summable, that the kernel at 0 is 1. Okay. Use these conditions. So we're done with term 1. We are done with term 2. Okay. So all that is left is term 3, which is this term here. I have an extra slide in case I wanted to write something else. I don't want to write anything else there. So come back here. We have that this term over here is what I'm calling term 3. And here I'm going to define a new object that I'm going to call gamma star, which is just the expected value of the gamma hat, which is equal to this. And why? So we're saying this gamma hat is biased for gamma j. Why? Because as Felipe said before, we're not dividing by n minus j, we're dividing by n. If we were dividing by n minus j, we wouldn't even need to do this. But this is not going to be a lot of complication. So I'm going to take this term over here. And so I'm going to say term 3 is equal to the sum of j negative mn, the kernel, and gamma hat j minus gamma star j plus the sum same indices, kernel. Now the difference between gamma star j and gamma j. This guy, this term goes to 0 as n goes to infinity by the same arguments, or I should say similar arguments to those used for term 2. Essentially, the dominated conversion theorem. So this is, I'm going to write here, easy, done. This guy will go to 0. And it's non-stochastic again, because gamma star j and gamma j are non-stochastic. The question is this guy. And so this guy now, which is the remaining object, is less than or equal than the sum of gamma hat j minus gamma star j. And so at the end of the day, the proof is complete if we show that this converges in probability to 0. This is what I'm going to write here, want to show. And if we show this, done. We completed the proof. So we split the proof into several steps. We split it terms 1, 2, 3. 1 and 2 go to 0. 3 only depends on this object, and this object is bounded, okay, by this guy. So all that we need to do is to show that this sum of the absolute value of gamma hat j minus gamma star j goes to 0 in probability. Okay? And this is what I'm going to do next. Are we doing well up until this point? I guess that's a yes. So let's start work here. We want to show that the sum, this is what I had in the last slide, that this sum goes in probability to 0. And here's where I'm going to use this strange condition that we had in the statement. Condition number 3, we had that. So step 1, I'm going to define this zeta ij, as I did in the statement of the theorem, as eta I times eta I plus j minus gamma j. Okay? And we're going to show in this step that the expected value of gamma hat j minus gamma star j squared is bounded by c divided by square root n. Okay, so let's just do that. I'm going to write expected value of gamma hat j minus gamma star j squared. This is equal to, I'm going to say here, note 1 over n, the sum from I to n minus j, zeta ij is equal to gamma hat j minus gamma star j. Okay, this is by construction, we constructed this eta j that has this property here. So then this is the expectation of 1 over n sum I1 to n minus j eta ij squared. And so if we work out the squares, sorry, we have that this is 1 over n squared sum I1 n minus j sum k1 n minus j, and the expectation, if you want, the covariance of eta or zeta ij zeta I k. And so here we have that this sum, a sum over k of this covariances, okay, with the absolute value. So maybe we can do another step. Let's just add the absolute value. This is less than or equal 1 over n from 1 to n minus j. This is wrong. This is eta k j. There we go. And I should correct this here. Zeta k j. Okay. That was a mistake there. Just make sure you correct that. So this object here is less than or equal to C uniformly over J and I by, let me just write that, by star. And this is the condition star. So this is less than or equal than C, or is less than or equal. There's a mistake. Here is an n squared. There's 1 over n squared. The sum from I1 to n minus j C. And this is equal to essentially C divided by n. And this is what we wanted to prove in this step. I wanted to prove that the expected value of gamma hat j minus gamma star j squared is bounded by C divided by n. And we did that by using this condition here, gamma star, or star, sorry, which is this uniform behavior of the sum of covariances. So C shows up. We have the n squared here. We're summing n of this, n minus j, but it doesn't matter. It's just n rounding. And so this is just C divided by square root n. And so we're almost there. We just need one step, because what we want to prove is that the sum of these objects, okay, converges in probability to 0. And we just show that the expected value of this object square is, bounded by C over n, which is mean goes to 0. So we are missing now the step where we want to use essentially Chebyshev's inequality. Okay, and so we just want to use this step into this type of result, and then we are good to go. And that's the last step of the proof. So again, we want to show that this goes to probability to 0, and that is, we want to show that the probability that this sum is greater than epsilon goes to 0. And we're going to use the previous result in doing so. The first thing that we're going to note is that this event that I'm calling here A, which is that the sum of this different on the absolute value greater than epsilon, implies the event B. Put it in a different color, B. Okay? So the event that the sum is greater than epsilon implies that this, guys, gamma hat minus gamma star is greater than epsilon divided by 2m plus 1 for at least 1j. And why is 2m plus 1? Because those are exactly the number of terms that we're summing, right? We have m to one side, m to the other side, and the 0 term. So you have 2 times m plus 1. That's for the gamma 0. And then you have m to one side, m to the other side. So you're summing 2m plus 1 objects. And so saying that the sum is greater than epsilon is the same as saying that at least one of these, guys, is greater than epsilon divided by the number of terms that you are summing. Okay? And we're going to use this then, because I'm going to say the probability that the sum from j negative mn to mn of gamma hat j minus gamma star j greater than epsilon is less than or equal than the probability of the union j negative mn of this event, which is gamma hat j minus gamma star j greater than epsilon to mn plus 1. Because at least one of these j's is greater than that. And now we use Bonferroni's as we did last time. This is the same, less than or equal than the sum from j equals negative mn of the probability that gamma hat j minus gamma star j is greater than this. I'm going to write here by Bonferroni the probability of the union less than or equal than the sum of the probabilities. And now this is less than or equal than the sum from negative mn to mn, times the expected value of gamma hat j minus gamma star j square times 2mn plus 1 square divided by epsilon square by Chebyshev's. So here's the step where we use Chebyshev's inequality. And now we can use the result that we had for the object in the last step, which was about this expectation. So this is less than or equal than the sum, or I'm not going to have space, so I'm going to do 2 steps in one. So, okay, let me be more clear. This, we know that is less than or equal than c divided by square root n. That's what we did in the previous slide. And nothing here depends on j anymore. So we have here 2mn plus 1 terms. So if you put those two things together, this is 2mn plus 1 terms times c divided by n times 2mn plus 1 square divided by epsilon square. And this is roughly c divided by epsilon square times mn cubed divided by n. This goes to 0 by our assumption that m cubed divided by n goes to 0. And that's that. That's the end of the proof. And we show with a lot more work than in the other case that the HAC covariance estimator is consistent. So a few comments before we conclude today's class. We prove consistency, but not prove positive definite of our estimator, okay? That, of course, was done in the original papers. I'm just not going to get into that because, as I wrote here, requires to characterize this estimator using a Fourier transformation, which I'm not going to do. But you have to believe that that's the result. The other thing is, in order to implement this, you need to have a bandwidth choice or a truncation lag choice. This mn, you need to choose in finite samples, okay? So if you want to estimate this estimator with a software, you need to provide mn, which is called the truncation lag, okay? So then, there was a lot of work done on this at some point, and in particular, Don Andrews wrote a comprehensive paper about how to choose mn by essentially minimizing mean squared error. And the general idea is similar to the ideas that we have in other bandwidth, that there's a bias variance trade-off, okay, which we discussed. A bigger m reduces the bias, okay, but it increases the number of bad covariances that we're using. That is the variance. And so the idea is that if you just characterize the mean squared error of this estimator, which, believe me, is sort of like a really ugly expression, okay, then you have, of course, the bias squared times the variance of this, and then you minimize this with respect to this thing mn. Well, Andrew showed that the optimal truncation lag is a constant c star that depends on all these objects that you can estimate, and its rate depends on the kernel that you use. For example, in the case of the Bartlett kernel, r is equal to 3, so it's n to the 1/3, okay? But for other kernels like the quadratic spectral, for example, r is 5, so it's n to the 1/5. And then the paper also provide expressions for this constant c, and these things have been, they're old, as you can see, 87, 91. They're already packaged pretty much everywhere. So like even Stata, you just write, and then we'll compute the truncation lag using these results by Don Andrews. And if you look at the packages in R that do the same, they're gonna be using this. Sometimes there are no options and people use HAC covariance estimation, but very often in finite samples, the performance of these standard errors is quite poor. Okay, so People in time series have long discussions about this and what to do. But in the context, if you're more coming from an applied micro person that sometimes runs regressions where there's like time series, unless you're just dealing with a time series regression, okay, most often you will want to do something else than to use these HAC standard errors. The results tend to be quite sensitive to this M business, okay? So you can, if optimal M in the Andrews approach is equal to 4, and then you just say, okay, let's try 5 and 6 to see how the results look like, okay, you're going to see that the results sometimes can change a lot, okay? And there are a lot of simulation evidence that show you that this standard error is typically really undercover, okay? So you really want to have a 95% confidence interval, when in reality, using these standard errors, you're getting an 80% confidence interval, 60% confidence interval. And the more heterogeneous and dependent the data is, the worse they work, okay? And again, if you could choose magically a really nice value of M, then they will perform better if you use some oracle thing. But since you have to choose M in finite samples, it makes the implementation of these methods more complicated. So again, they're not difficult to conceptually. I think it's quite simple what these HAC covariance estimators are doing, but in practice, they can be quite challenging to tune. Of course, you're not going to know that. You're just going to have a given application. You're going to choose M, and the computer is going to report a number, okay? So whether that is working well in the context of your application, you're not going to know. So when I say that they perform quite poorly, it's mostly based on simulation evidence, of course, okay? And that's about it for today. So it was a long proof relative to other proof we've done in the class, but hopefully it just highlights the elements that I want you to keep in mind so that you understand the mechanics of it behind. And, next class, we're going to talk about cluster robust standard errors, which is another way of dealing with dependence. But for now, we're done with today, and I'm going to move to answer questions.